Hello and welcome to the next lecture in the course. What I'd like to do today is talk a little bit more about our laboratory, the Centre for Machine Vision, which, as you know, is in the BRL in T Block. So this little presentation here, I'll just go from the front on this one. And so the title of this was Our Part in the Intelligent Machine Vision Revolution. And really talking about how AI and vision can come together to enable you to do some pretty difficult and previously considered intractable tasks. So there's the little icon that we use for this presentation, and we're asking how can machine vision and learning help humans? And one possible answer to that is that we can realize devices that gather richer data, which is something I've been talking about in recent weeks. So that means combining 3D with 2D data and then learn from experience. And we're also making use of the latest developments in equipment. Of course, one thing being the 3D cameras. Now, there's lots of different types of cameras which I talk about in the course and you'll be aware of. But one of the most useful ones, due to the fact that it performs quite well, is quite low cost, is the RGB-D camera. RGB for red, green and blue, and D for distance. So it gives you range data. I mean, this was originally developed for the Kinect, which was an interface device for an Xbox, as you know. And of course, that was Kinect version 1, which was, when that was released as a sort of device to be used in any kind of research, it really was used by everybody. And there was loads of papers coming out. I was doing special issues of journal papers. I was a guest editor on things like 3D machine vision. We did one. Another one we did was outdoor machine vision. So the Kinect was a bit of a revolution in gathering 3D for use in machine vision. And then, of course, there was a Kinect version 2, which works slightly differently from Kinect 1. And I would recommend that you look this up on the internet, because there's a lot of information on the internet about how the Kinect versions 1 and 2 work. And it's quite interesting. And the technology has, of course, been taken on by other companies like RealSense, who have their own version of the RGB-D camera. And then what we do is that we combine that really with AI in the form of deep learning, which has got to do with the convolutional neural networks that I've been talking about. So what have we done in the past in our lab? Well, we've developed systems for clients all over the world in all sorts of different sectors. QB-Scan, Petroscope, long-range 3D camera for security applications. How's My Cow, which is, I'm here in Somerset and it's being used in here and around the country. Grass Vision, which is being used in Scotland with a company. Harvest Eye, which is being used by Branston, which you probably might not have heard of as a company, but they're the biggest potato producer in the UK. And they're based up in Lincolnshire mainly. That's where Branston is. And they have commercialised the system we developed for them, which measures potatoes as they're being dug out of the ground on a harvester. It's the first system that we know of that's capable of doing that. Then the UWE skin analyzer is something I'll talk a little bit about. PhotoFace, again, it's 3D face recognition. Then we developed the non-contact wheel alignment system for the client in India. This is just some of the things. We've done more than this. This is just some of the systems that we developed over the years. We've been running this lab for over 20 years, so we've got a lot of experience. And of course, the system for tickless towel on the London Underground was pretty successful and is now operating in a research laboratory in Farringdon in central London. So new companies, cow condition lameness monitoring, 3D potato metrology in the field, weed detection in grass, 3D skin detection for detection of cancer. Yeah, just recently set up a company to exploit the skin analyzer. It's just finding the right resourcing and funding chain to actually take that forward is usually a problem, especially in medical applications, actually, for various reasons. A very conservative field, I would say. So far, 12 patent applications. So I might have shown you this slide before, but this is what we're talking about in machine vision with our industrial camera, hardened in a metal case usually, with a standard lens attachment and a whole range of equipment coming from these suppliers, and then interfaced to the computer, of course. And then this is some graphs. This is for the non-contact breathing measurement NIHR project that we did about 2012, which was pretty successful. The face recognition for pigs is operational, and you can see a heat map showing the area that the network concentrates on to differentiate between the pigs. And that's a demonstration of our 3D face recognition system for the London Underground. You can see there the Wenhao, you can see that it's picking up all the difference in orientation of surface normals over his face, whereas for the photo it's all pretty much planar. So you immediately got robustness straight away. You can differentiate between a real person and a photograph. So 3D face, going on to what we're talking about, there's 3D face recognition acquisition. And the first time we got into this in a big way was in 2007 with General Dynamics and Imperial College. And we had quite a large grant, I think it was £500,000, for developing a thing called PhotoFace, which is still operational now and captures a series of images with the face as you walk through it being illuminated from different angles. And you can see, I mean, this is Mark walking through the device, and you know, there's no difference in his face between these different shots. It's all taken in a fraction of a second. But you can see how different he looks, just depending on the direction of orientation. It shows you how important the lighting angle and conditions are for something like face recognition. Here we got what we call the bump map, where we got a dense array of surface normals over the face, showing the orientation of the face at all positions. And then we can integrate, because this is basically gradients over the face we're talking about here. We can integrate that to go back to the actual 3D cloud points, if you like, or position data of the face, morphology in 3D space, and that's what we've done there. So this technique then, photometric stereo, we've applied it to a whole range of sectors. This is just one application. It seems to be very useful in all sorts of different applications. And this shows how we had a project with the MOD where we were removing camouflage. So we made this mask up and covered it in paint, all this camouflage paint. And you can see all the paint was on it. We applied our technique and we've immediately, and you can see all the camouflage on the back surface here. That's still on this surface, just it's been removed by the technique of photometric stereo. And here we had another sheet of material and we put some little models on it. Got plastic models of things like vehicles, and actually this was more like a sort of to do with army equipment, like a canteen and so on. And you can hardly see it because it's camouflage, but when you remove the camouflage, you can see these things quite clearly. I mean, when Abdul was working with me on this, I was saying I was sending emails to him saying, "Don't forget to bring the guns in." So I just hope that nobody intercepted it, because I was on about the plastic guns and Toys R Us for this demonstration, you see. Okay. And anyway, so here we go. This is a RealSense camera I was talking about a minute ago. And then we've got the thing, you can, just what that's that thing I showed you a minute ago, what it actually looks like with a normal photograph. So here we can remove that camouflage, and then we can orientate, we can get this thing recovered in 3D. So you can see that you can look around it and examine it in quite a lot of detail, as we're shown here in these videos. It's just the shape of it, okay? And then you can get, what you can get with the RealSense camera is kind of the general shape of it. Then you can use our technique to get this high frequency texture data, and then you can put that on and you can see over here that you're getting a pretty realistic visualization of having a look at this thing. But this is virtual. This thing is just in the computer memory in this case, but it looks like you're with it and having a look at it. So PS preserves high resolution data, but it isn't so good at recovering global geometry. Some errors can creep in with photometric stereo when you're trying to recover the actual shape in 3D, but it gives you that texture very well. Contrast, these depth cameras give you the general shape, but they don't usually give you the fine detail, because they use sort of projected patterns typically, for example, for triangulation for recovering the shape. And the texture with which you can recover, and the resolution which you can recover that, is dependent on the nature of the projected pattern. So case studies, got a few case studies. Now we started off back in 99, 2000 with a project for a company called Quantronics in Salt Lake City, and their application was actually objects on pallets. So these, I don't know if you know, but when you get on an aircraft, under the seats there's loads of air freight which is on these pallets. And nowadays it's not so much about weight, it's more about, well, obviously you don't want it too heavy, but it's not about exact weight, it's more about the area, because a lot of high-tech stuff's being transported around. And so they want to know the volume equivalent kilogram, in other words, how much volume is equivalent to a kilogram for their costs. And so they asked us to measure the dimensions. Of course, being American, it was all in feet and pretty huge. I mean, I think it was 6 by 6 by 8 feet high, what they were asked to measure. Which doesn't sound that bad, but when you see something like that, it's enormous. It's actually pretty enormous, when you get it in the lab. We managed to make this for them, and they actually installed it in the UK, in Bicester at the MOD, and they told us of so many million sales when I asked them one time. So they sell quite a few versions of this system. So the idea is it hangs from the ceiling here, you see. It's completely non-intrusive, and it measures these objects underneath before you put them onto the aircraft. It's the kind of thing BA do at their World Cargo headquarters at Heathrow. 3D characterization of aggregate petroscope. And project for Petromodel Limited, Iceland. System to measure. This was a system we developed for a company in Iceland. I went to Iceland. It's quite interesting, Iceland actually. But to measure aggregate, and it's called the petroscope. So the idea is that you're mining this aggregate for road making or whatever, and you want to make sure you're getting the right kind of stone. If you get the wrong kind of stone, you're digging a big hole for nothing, which is bad for the environment. At the moment, they send the stone off. It takes about a week or two to get a result. But with this, the idea you have this system in the quarry, and you're monitoring as you go, and got a patent on it. And they had nothing before they came to us, and we developed this system for them, so it was quite good. Got some nice papers out of it, actually. You can see here we're using laser triangulation, and we got this here. The brighter bits indicate they're higher near the camera in that visualization. Then one time a student said to me, his father ran a company in India, and he wanted to do a project. I thought, oh well, yeah. Is that really true? And it turns out it was, because we did, I think he paid us £100,000 eventually, and we developed the system. Now this is a non-contact wheel alignment system. So if you go to a garage, they do a wheel alignment for you. You might notice they hang these things on the wheels, on the tyres. With this, it's completely non-contact. So there's no contact at all with the vehicle. So these towers here contain specialized lights and laser triangulation that we developed for them. And it works, he's now selling it in India. And it works pretty well. It was a big challenge, as you can imagine, to get the accuracy for the kind of wheel alignment that's needed. But, we managed to do it for him. Actually, with this project, he said to me, near the end of the project, what about the run out? I said to him, what's that then? And he said, what you've got to do is, apparently in India there's quite a few potholes, and there's a fair chance that the wheel's buckled. So if you align the wheels, maybe they're not aligned due to the buckling. So what you've got to do is, once you've aligned them, is go out, drive the car around, come back in and do it again. So we accommodated that for him, and now he's got it working. He's selling it. Now, windscreen cracks, we had this project for Autoglass, and this was a very nice project, but always get difficult projects, as you notice. I mean, you can see that we're trying to detect these cracks in the presence of all this busy background information in the image. The idea here is that someone gets a crack, and they phone up Autoglass, and they send an email or whatever, and they send an email with a photo like this. And then the engineer or guy who's doing it can work out how much filler to bring and how to deal with the problem before he gets there, because making it all quicker and easier for them to do. And so we had to segment the damage in the windscreen to prevent it turning into a bigger damage. You want to prepare it. And it worked. You can see that we're segmenting these fracture damage and these stones hitting the window here. And they were quite happy with it. And that was quite nice. A good company to work for, actually. Now, the photometric stereo, as I mentioned before, is a system whereby you walk through this device, and this is the device that Gary built on it, and there's a camera there, as you can see, and that's a high-speed camera that captures many images a second, hundreds in fact, and it's synchronized with these lights. In fact, these are LEDs. These are near-infrared LEDs, so you don't know that it's operating. It's a sort of discrete system. You don't want real light, because flashing lights could be a hazard for some people with epilepsy or something. That point of view. So this is pretty safe. You can't see anything. It all happens in a fraction of a second. When you walk through, I think this image is quite good. This is Juai, who used to work with me quite a bit. And very good. He did some great work on various projects. But you can see here that it's picking up the skin textures with pretty high resolution, beyond what you'd be able to get with most other systems like RGB-D cameras, really. So then this opens up an interesting opportunity for biometrics. For a start, this shape and the relative orientation across the forehead and the nose are quite distinctive of an individual. We did a research project on it and published a paper, and it captured the people's imaginations, actually. They got me on the BBC in Bristol talking about it. And it would have worked, it's additional biometrics, so we could have had it on an ATM to verify, or it means you wouldn't have to use a PIN, perhaps, that kind of thing. And so it's removing the contact, especially I think that's important in COVID-19, because you don't really want lots of contact all the time with this virus and the chance of passing it around. So another system we developed with that in mind as well was this palm print reader, which works and gives you a pretty high resolution palm print, as you can see here. and it uses photometric stereo again. So this is non-contact recognition, and it's useful for applications like gyms and places where you want to get into certain secure rooms. But you don't want to mess around with this fingerprint reader. I don't know if you tried using those things, but they're a bit difficult to use. And suppose you're in a gym, you use it on and you go in, you do a big workout, your skin's changed because of the hydration of the skin. And so it's no good, it may not work on the way, next time or the way out or whatever. So non-contact's better. And a nice paper out of that, which we're going to publish, and we're trying to get a project on to commercialize it as well. Now this is a skid analyzer, which we've been working on for about 18, 19 years in the lab. And that's a Mark II, and this is a Mark III that Abdul designed. And you can see there a typical image, it's a little dark that image, but you can see this capture of a mole there. So what we're doing is looking at moles with this to try to work out whether they might be suspicious and any chance of turning into cancer. And so what we could do is, again, we're applying photometric stereo. So we've got the albedo, which is like the color of the mole. We've got the bump map, which is like a 3D visualization. As you can see, we've very robustly separated the color from the actual shape of the mole. So with this, we can move the virtual light around and we look at this thing from different angles. And that's the kind of thing the doctor would do if he was actually with a patient. He might not think about it, but that's what he'd be doing. He'd be moving around, changing the light and seeing what it looked like. Then we could combine the albedo and the rendered image into a virtual interactive visualization. So this is a bit like for the doctor as though he's there with the patient. He can move the light around, he can change the viewpoint. There's another one here. So this has got potential to really accelerate teledermatology, because at the moment teledermatology is not considered to be much use, because all you're doing is sending emails of pictures, and every time you take a picture, everything looks different because the light's changing and the camera position angle. So this could be a bit of a revolution in teledermatology. I think that's what the main motivation for this is, along with the idea of capturing these moles. Because at the moment, people who have moles who are worried about it, they go to the doctor. The doctor doesn't have much training in it because it used to be quite rare. So he just sends everybody to the pigmented lesion clinic in Southmead. So the clinic is completely overloaded, and anybody who does have something wrong with them might stand a good chance to be masked by all the people who've got nothing wrong with them. So if we can get something to help the GP to refer more accurately, then this might save lives, really, because we capture conditions earlier and we'd avoid those problems. We save a lot of money for the NHS as well. So another system then that we worked on is, of course, How's My Cow, which is this very nice project which worked very well and is now operational around the country. Arla, in fact, are buying into this. So you can see that this system measures the cow in 3 dimensions as it walks under a walkway off to the milking parlour, for example. So we're getting all this 3D data. So we had a specialised and our own unique technique, as well as the 3D data. We had a technique for analysing angularity. We actually developed it. In the project I described for Iceland, okay, the Petroscope project. We developed it for looking at aggregate. We suddenly realised it would also be useful for working out the angularity of cows. So we use the same technique, and the more angular it is, the more bones are sticking out, the lower the condition score is. So you can get sort of a more objective measure of body condition, which is useful for the farmer, because he wants to know what the condition of the cows. He wants to optimise it for milk production. And cows are quite canny animals, because if they got something wrong with them, which apparently quite a few do, between maybe 10% of them have got something wrong with them and they're lame at any given time. They're pretty good at noticing when the herdsman's coming, and suppose they're limping, they'll stop limping, if you can imagine that. So so this system, obviously, this doesn't apply for this system. So we're also able to detect lameness, and obviously the cow wouldn't know whether it's operating or not, so it's not able to avoid detection. And that benefits the cow, actually, because there's more chance of putting it right without having to cull it, and it saves the farmer money. So it's quite a nice project running all around the country. That one's commercialised quite well. So I had a lecture on neural networks, I believe, but this is a presentation I give to people, and I talk about this. So this is just talking about what you've probably seen in the lecture before, a neural network, and I talk about it because it's a pattern recognition technique which is so powerful and so useful nowadays in all these complicated applications. So this is talking about how the network works. As you know, feed forward, back propagation. You feed some data in, it goes through, multiplied by these weights, it goes through these neurons, you get an answer out. You look at the error, but in other words, the difference between what the network's saying and what the data should be according to the training data, the outputs. And then you modify, the system modifies iteratively these weights so as to minimize the error. And that's how a neural network works in a nutshell. It's called feed-forward backpropagation. That's the simplest type of neural network. And remarkably powerful and useful. So, and again, going a little bit further, we go to deep learning. We use this idea of convolution for, and as you know, convolution is useful for automatic feature identification, and it gives you better accuracy on when you've got variable data with lots of variations in it, like you get in the real world. It's much more reliable and able to capture and recognize patterns than just about any other technique, really. Deep learning is very powerful. I mean, other techniques are quite good, but this was a breakthrough when they started, when they got it working seriously in 2012, I think it was. And so it simulates the human eye. The convolution simulates the human eye, visual cortex a little bit, and then the neural network part towards the back of the network is fully connected. So that's more like a conventional neural network. So that's where classification. So feature identification with convolution, and then classification later on to say, is it a dog, is it a cat, whatever it is you're looking at, trying to classify. And of course, the pigs was a good one. And it's an ongoing project because, as I mentioned in one of the previous presentations, the face recognition for the pigs works pretty well. And if you take a system developed for humans and then just retraining it a little bit, that works quite well. To us, all these pigs look the same, but they're actually quite distinctive, just like humans are. Just so our eyes and brains are not tuned to recognizing pigs particularly. So yeah, these are some of the nice results we got. We got with our CNN 96.7 accuracy, pretty good. Yeah, more pigs. All the time we're increasing the number of pigs and seeing if we can maintain the accuracy, which seems to be quite promising so far. There's a heat maps to these different characters, and the more red it is, the more of interest it is to the CNN. And avoid using other features in the image. It might be telling you. You've got to be careful all the time with in machine vision that when you're doing all this, you don't have something else going on in the image that the network might be using to work out what's just to classify rather than the actual thing you're interested in. So that's always a challenge. And then the underfloor spraying of the, in Britain, obviously there's loads of material of sort of Victorian buildings, and there's a lot to be heat lost through the floors. So if you can start spraying this insulation underneath, you're going to save people a lot of money. And our system worked pretty well with a neural network, with a CNN, for segmenting different objects under the floor. Gary did a nice little project on that, got a good paper on it, that one. Segmenting floorboards, all the different features of interest. And of course, the leaf segmentation, what Gitis did his PhD on, works very nicely. And we've got ongoing projects with the University of Edinburgh with their growing facilities. Flew up to Edinburgh to talk to them about it a few times. And very nice projects. Weed detection, one of my favourites, because in Somerset here we get these enormous dockweeds. I swear they're bigger than the ones in Scotland, to be honest, but there we are. I mean, if I could get this working in my garden, it'd save me a lot of trouble. But so we're trying to identify automatically these dock in the presence of grass, and we're spraying that herbicide just exactly on the weed. And in the paper that I put online, which is definitely worth having a look at, it's quite a nice, I think it's quite a good introduction to deep learning in terms of the history of it and where it came about. And it also talks quite well, I think, if I say so myself, about transfer learning and data augmentation, which are techniques it's worth being aware of, quite important techniques in deep learning. This little video might show the weeds coming along and system identifying them. Here we go. Images, we're going along the field, coming along. Have we got a weed? Yeah, there's a bit of weed there. There we are. This has been automatically identified by the system. We're getting something. So, you're talking about small amounts of dock, which even humans have. It's not obvious to sometimes, but can be quite harmful to the animals. We're trying to segment it. There's a dock. The system's automatically segmented it now. Now, another little project, which Lily, who now works for Dyson, actually, she left the UWE and worked for Dyson, but she did some good work and was working on was a very low-resolution thermal sensor array, which we use instead of a camera. So this would be for people at home, for example, who you might be worried about. You might be worried about whether they're going to get into distress, or there might even be a fall potential or something like that. So with this, you've got very low resolution, and so it doesn't invade their privacy. It's obviously contactless, and the data coming from it is nice and simple, being low resolution. but it's accurate enough to detect daily activities. So even though it's very low resolution, you can differentiate between different things that the person's doing at home. So that was really quite a nice little project she did there on that. And she compared the handcrafted feature-based method, in other words, trying to dream up what features are manually and then use that, compared to using the 3D neural network-based method. And you get a much better accuracy, wasn't she, really? Especially with things like stand still, sit still, stand to sit, walk left to right. She was getting an improvement apart from that one, just about everything else. Overall, significant improvement, I think you'd say. So these are the kind of images that she was getting of different. This was a sit still situation, for example. And yeah, so this is some of the data that she got, which I kind of liked. I might take that forward because it's quite a nice one. Especially this kind of thing is useful in COVID, of course, because when there's a pandemic on, you don't really want people traveling around checking on people continuously. If you can monitor them remotely or through the internet using these kind of techniques, then you're really cutting down the chance of spreading the virus. So to summarize then what's going on in our lab, machine vision uses 2D and 3D, and in our lab a fusion of both a lot of the time. And we combine state-of-the-art hardware with sort of advanced software and image processing, feature recognition techniques to get sort of useful results in difficult situations. And we found it's possible to measure the dimensions of an object accurately in a well-constrained and calibrated environment. And that's the kind of thing we have done. We're finding it's more and more possible to get good performance in unconstrained environments as well. 3D data allows for easy segmentation of foreground from background data. So that's quite important. If you know the range, you're looking at something in the foreground, then you get rid of everything that's over a certain range away, because even if it's busy, the background, you can just get rid of it, and this makes your life easier when it comes to processing the images. Machine learning allows for pattern recognition as opposed to metrology. Okay. Defect detection versus length, width, dimensional measurement. I mean, it depends on what you're trying to do. If you might be trying to detect a defect, or you might have some important product characteristics you want to try and accurately measure for various reasons. Deep learning provides a previously unseen robustness in real-world environments. I really think that's true, especially outdoor, for example. I mean, when you look at papers on agritech, nearly all the work's being done indoors, and it's all being done indoors and in a laboratory where everything's controlled. But what we were interested in is going out onto the harvester in Lincolnshire, where they got rain, lights changing, clouds, everything going on, bouncing around, vibrating like anything as well. And then still getting useful data. I think we demonstrated that. They're using it right now. That is easy to underestimate the difficulty and importance of doing that. Just taking something into the real world is a massive challenge. But with deep learning, with some of these robust systems, I mean, the system we installed on the harvester, it took us several months, I don't know how many months, just to make it rainproof. And it's also true of the cow system as well, because the farmer will put a hose pipe on it and so on, and you've got to make sure that you've got to get the heat out as well as make it completely waterproof, which a lot of the time actually put it in a metal box is the answer to that, surprisingly. We looked for about 2 months at all sorts of heat transfer equipment, heat pumps and so on. We realized you didn't really need it, just some fins and a metal box would be a lot of the time help, but we do everything you need. Anyway, if anybody at the time wants to talk about research projects or they've got any ideas, you can always drop me an email, because we're always looking for new contacts and we're always getting new things going on. So I hope that was useful, giving you a little bit of background on where we're coming from in our lab. Next week I'll probably go through a few more details next time, maybe talk about a few extra things, but I think that was hopefully giving you an overview of where we're coming from. So thanks for watching, and I'll see you again.